In this class, we are going to learn some concepts of thermal physics, and we are going to solve a good problem based on those concepts. Okay, so first of all, I will show you the book which we are going to refer, and the problem also which we are going to solve in this class. Just a minute. So this is the book which we are going to refer. The book is, publication is Cambridge University Press, and the name is Physics for the IB Diploma, 6th edition. Writer is K.S. Okoj. I will show you the writer's name also. See, the writer is K.S. Okoj. So we are going to follow this book, and we are going to solve one good problem from thermal physics chapter, and which problem we are going to solve, that also I am going to show you. So this is the problem which we are going to solve. This problem is from thermal physics chapter. What is question? A sample of 120 gram of solid initially at 20 degrees Celsius is heated by a heater of constant power. The specific heat capacity of the solid is 2500 joule per kg per Kelvin. The temperature of the sample varies with time as shown in figure 3.6. So this is figure 3.6. Use the graph to determine the power of the heater, the melting temperature of the sample, the specific latent heat of fusion of the sample, the specific heat capacity of the sample in the liquid phase. So these are the four parts of this problem we have to solve, and that also we have to solve on the basis of this graph. Okay, so now we'll come to the problem later on. First of all, we'll learn the concepts of thermal physics, mainly thermal properties of matter. Okay, so first of all, we'll learn about a specific heat capacity. A specific heat capacity. What is the specific heat capacity? The specific heat capacity of a substance is the amount of heat required to raise the temperature by 1 degree Celsius for the mass of 1 kg, and is denoted by a small letter C. The unit of a specific heat capacity is joule per kg per degree Celsius. Okay, so here we are raising the temperature by 1 degree Celsius, and we are taking the amount of the substance as 1 kg. This 1 kg is very important, and the temperature rise of 1 degree Celsius, this is also very important. So for example, so we are taking the example of 1 kg of water and 1 kg of paraffin, means kerosene. So 1 kg of water and 1 kg of paraffin would receive same amount of heat energy for the same amount of time, but paraffin raises double the temperature. Hence, by definition, a specific heat capacity is, see, amount of heat required, amount of heat provided, the total heat energy provided to raise the temperature by 1 degree Celsius. Okay, so we'll divide it by change in temperature, and to raise the temperature by 1 degree Celsius for the mass of 1 kg. So we will divide it by the mass of the substance. Means a specific heat capacity is equal to total heat energy provided, that is Q, upon mass of substance M. Delta theta means change in temperature. So what is Q here? Q is the heat energy. What is M? M is the mass of the substance. What is delta theta? Delta theta is the change in temperature. Change in temperature. Okay, so a specific heat capacity of a substance, in mathematical term, it is Q upon M into delta theta, where C is the specific heat capacity, Q is the amount of heat energy in joules, M is the mass of substance in grams, but not here. Here we'll take the SI unit as kilogram. So here the m is the mass of the substance in kilograms, and delta theta is the change in temperature. So we already know that a specific heat capacity of water is very high compared to other substances. And the specific heat capacity of water is approximately 4,200 joule per kg per degree Celsius. So that is why, because the specific heat capacity of water is very high, that is why it is useful in cooling car engines. Now the second thermal property is thermal capacity. Thermal capacity or heat capacity also we say. Heat capacity. So heat capacity and a specific heat capacity both are different. They are not same. A specific heat capacity. A specific heat capacity is always defined for 1 kg, for 1 kg of mass of substance. But heat capacity for the whole mass of the substance. Correct. So what is the definition of thermal capacity? The thermal capacity of a body is the quantity of heat needed to raise the temperature of whole body by 1 degree Celsius. Okay. So this is the difference between the heat capacity or thermal capacity and a specific heat capacity. And this you have to always remember. Okay. So in this case, thermal capacity, mostly we denote it by capital C. Capital C is equal to m into a small c, that is a specific heat capacity, where m is the mass and a small c is the specific heat capacity. So thermal capacity or heat capacity is equal to Q upon delta theta. See here, what we are getting here, C. We have already defined C. C is equal to Q upon m into delta theta. Correct? And capital C means thermal capacity or heat capacity is equal to m into C. So write it here, m into, in place of C, we'll write this Q upon m into delta theta. So this m cancelled. So can we write it Q upon delta theta? Correct. So thermal capacity is equal to Q upon delta theta. Okay. Now internal energy. Internal energy is the energy stored in a system at the molecular level. That is its thermal energy. It is the kinetic energy of the atoms or molecules due to their random motion plus the binding energy or electric potential energy that holds the atoms or molecules together in terms of atomic bonds or intermolecular bond. Okay. So what is internal energy? Internal energy is the energy stored in a system at the molecular level, that is its thermal energy. It is kinetic energy of the atoms or molecules due to their random motion. So kinetic energy is always due to its motion plus the binding energy or electric potential energy that holds the atoms or molecules together in terms of atomic bonds or intermolecular bond. So this is internal energy. Now come to the latent heat. So latent heat of fusion. So when a solid substance changes its state from the solid to the liquid, energy must be supplied in order to overcome the molecular attractions between the particles of the solid. Means if you are having 1 kg of ice, you want to convert this 1 kg of ice into 1 kg of water, then you will have to supply heat here. Okay. Okay. And that heat will be utilized in breaking the molecular attractions between the particles of the solid. So this energy must be supplied. So here there is a change from solid state to liquid state. Solid to liquid. Okay, so this is called fusion. This is called fusion. And the energy required, the heat energy required, that is called the latent heat of fusion. That is called latent heat of fusion. See here, if this is solid, the molecules or atoms are very closely spaced. They are bound, here the binding is stronger. And then when you supply the latent heat, then what happens? This, whatever the energy you are supplying, that energy is being utilized in breaking these bonds. So now in liquid state, your molecules are separated and they are in this state. So externally, normally as heat and does not change that here. So here the phase change. So this is called change of a state or phase change of a state or phase change. So this phase change or change of a state occurs at constant temperature. Means whatever heat energy or energy you are supplying, that energy is not being utilized in raising the temperature. The whole energy is being utilized in breaking the bonds between the atoms or molecules. Okay, means from changing the state from solid to liquid. So externally, normally as heat and does not change the temperature. So does not change the temperature means this change of a state or phase change occurs at constant temperature. We call this energy latent heat. The word latent means invisible because we are not able to see it. So it is the energy released or absorbed during a change of a state without increasing the temperature. So it is the energy released or absorbed during a change of a state without increasing the temperature, means temperature will remain constant. So just like the specific heat capacity, there is another term during phase change that is called a specific latent heat of fusion. So here also the specific latent heat of fusion is always defined for 1 kg mass. So the specific latent heat of fusion, LF, of a substance is the amount of heat energy required to convert unit mass of the solid into the liquid without a change in temperature. Okay, temperature is constant. So mathematically, latent heat of fusion is equal to Q upon M. Okay, just a minute. LF is equal to QM. So from here, we can also write this. LF is equal to Q upon M, means Q is equal to M into LF. LF stands for latent heat of fusion. Now latent heat of vaporization. So in case of latent heat of fusion, there was change of a state from solid to liquid. Solid to liquid. But here, in this case of latent heat of vaporization, here the change of a state is from liquid to gas. So the change of a state from liquid to vapor or gas at constant temperature also requires the input of energy called the latent heat of vaporization. So the change of a state from liquid to vapor at constant temperature also requires the input of energy called the latent heat of vaporization. This implies that while a liquid undergoes a change to the vapor state at the boiling point, so this change from liquid to vapor occurs at boiling point. And here this occurs at solid to liquid occurs at melting point. Okay. So this implies that while a liquid undergoes a change to the vapor state at the boiling point, the temperature of the liquid will not rise beyond the temperature of the boiling point. Here also means this change of a state is also occurring at constant temperature. Means during phase change from liquid to gas, there is no rise in temperature. The whole amount of heat is being utilized here in breaking the bonds. See, now this is the latent heat of vaporization. Another term we know that is called evaporation. Okay, see, this is another thing. So the latent heat of evaporation is the energy required to overcome the molecular forces of attraction between the particles of a liquid in order to break their intermolecular bonds and bring them to the vapor state, where such attractions are minimal. Okay. So here also the specific latent heat of vaporization. The specific latent heat of vaporization, LV, is the amount of heat energy required to convert unit mass of a liquid into the vapor without a change in temperature. Okay, now heating and cooling curves. See here, this is a very good example. See diagram on the left, not left, actually right. Here, this. The diagram on the right shows the uptake of heat energy by 1 kg of water as it passes from ice at -50 degrees Celsius to steam at above 100 degrees Celsius. So this point is 100, more than 100. This is 100. This is above 100. Above 100, you can say. Above 100 degrees Celsius. So the diagram on the right shows the uptake of heat energy by 1 kg of water as it passes from ice at, so beginning, what is the initial temperature? -5. So at -50 degrees Celsius, water will be in which state? It will be in the solid state, because at 0 degrees Celsius, water freezes into ice. So when it will go down, it will remain ice only. So 1 kg as it passes from ice at -50 degrees Celsius to steam. So, and at 100 degrees Celsius, the water boils. So at boiling point, the water is converting into steam. So above 100 degrees Celsius, water cannot remain in the liquid phase. It will be in the vapor phase or gas phase, gaseous phase. So, or steam also we say. To steam at temperature above 100 degrees Celsius affects the temperature of the sample. So see here, A, rise in temperature as ice absorbs heat. So what happens here? This is one A, this is B part, this is C part, this is D part, and this is E part. Okay. So what is happening here in A part? In A part, the temperature of the ice is increasing. The temperature of the ice is increasing. The ice cannot melt below 0 degrees Celsius. So ice will melt at 0 degrees Celsius. Means the initial temperature of ice is -50 degrees Celsius. So we will have to supply heat to raise the temperature of this ice. So when the temperature of the ice is increasing from -50 to -25, -20, then -10, then -5, and then 0. So when the 0 degrees Celsius is reached, at this temperature, melting of ice starts. And this melting, the whole melting process, this will continue until the whole ice is being melted. Okay. So at this point, there will be no change in temperature. There will be no rise in temperature. That is why this line is parallel. This line is constant. This shows that this is occurring at constant temperature. See here, this y-axis, the temperature is on the y-axis in degrees Celsius, and the heat absorbed in kilojoule is on the x-axis. So constant temperature. And here the phase is changing from solid to liquid. So this is fusion. or melting also you can say. Okay. Then what happens now at here when the B ends, then here all the ice has been melted. Now the water is in the form of liquid. So now whatever the heat you are supplying, that total heat is being utilized in raising the temperature of the water. So that in this C part, the temperature of the water is increasing, and then it reaches from 0 degrees Celsius to 100 degrees Celsius. This is 100 degrees Celsius. This is 0 degrees Celsius. So from 0 degrees Celsius to 100 degrees Celsius, water will remain in liquid phase, liquid state. And at 0 degrees, this is 0 degrees Celsius is the melting point of ice. Or this is the same as freezing point of water, you can say. Here at 100 degrees Celsius, water, this is the boiling point. Boiling point of water. So here water starts boiling. Then it means the liquid is converting into steam or gas or vapor. So here the water starts converting into steam, and this process continues until the whole amount of water is vaporized or converted into gas. So see, here there is no change in temperature. This also occurs at constant temperature because this is a change of phase. Constant temperature. Okay, and because here the change of a state is from liquid to gas, so that is why it is called latent heat of vaporization. This is the vaporization. Okay. Then after that, at the beginning of E, your whole amount of water has been converted into steam. Now, whatever heat energy you are supplying, that total heat energy will be utilized in raising the temperature of this steam. So now the temperature of the steam will go on increasing from 100 degrees Celsius, and here it is more than 100 degrees Celsius, means it can be 120. Okay, 120, 125, whatever it is. So A, rise in temperature as ice absorbs heat. B, absorption of latent heat of fusion. C, rise in temperature as liquid water absorbs heat. D, water boils and absorbs latent heat of vaporization. And then E, again the temperature of steam is increasing, rise in temperature of the steam. Steam absorbs heat and thus increases its temperature. See, the above is an example of heating curve. This is called heating curve of water. So one could reverse the process and obtain a cooling curve. This is called. So when you are going in this direction, okay, then this is called heating curve. This is called heating curve. And when this direction is changed, means you are going from like this in this direction, it is decreasing. So that is called cooling curve, nothing else. This is called cooling curve. Just reverse of that is called the cooling curve. Okay, so now we are going to solve the problem. Come to the problem. Okay, so this is the problem. A sample of 120 gram of solid initially at 20 degrees Celsius is heated by a heater of constant power. The specific heat capacity of the solid is 2500 joule per kg per Kelvin. The temperature of the sample varies with time as shown in this. So what is given here? The mass of the sample is given. Mass is what? 120 grams. So that will convert into kg. Okay, because everything is given in here in the, this is SI unit. So this is the mass. What is mass of the substance is? You don't know. What is the substance? It's in solid state. It is 120 gram, means 0.120 kg. Okay. And then initial temperature, you can say Ti, you can say, or T1, you can say. T1 is equal to what? In this case, 20 degrees Celsius. Correct? And the specific heat capacity of the solid is C, small c, equal to 2500 joule per kg per Kelvin. Okay. Now we have to find the power of the heater. Now come to the figure. See here. Here initial temperature is 20 degrees Celsius. And then this curve, this straight line shows you that the gradient is increasing, isn't it? It means the temperature is increasing. So it means for this line, this is the temperature rise. Temperature is rising. Means the solid is here from this here it is in the solid phase only. It is in the solid phase only. And the temperature of the solid is increasing. So it increases from 20 to, see here, this is 50, so this will be 48. 48. So final temperature T2 is equal to what? Here T2 is equal to 48 degrees Celsius. Correct? So what is the change in temperature delta T? For this part, you can say this is your A part. This part is A part. So for A part, delta T is equal to what? 48 minus 20 is equal to 28. Correct? So delta T is equal to 28 degrees Celsius. Now see here, this is the now this is the delta T, this is M, this is C is given. So we can find. So what heat energy, what is the amount of heat energy or electrical energy is here? Here one assumption we are making that there is no loss of heat to the surrounding. No loss of heat to the surrounding. Means whatever electrical energy you are supplying, that total energy is being utilized for heating the solid. Correct. So we can find this Q is equal to MC delta T. We have already seen this. So here M is what? 0.120 multiplied by C is what? 2500 joule per kg per Kelvin multiplied by 28. Okay. So we'll get, I have already calculated it. So I will give you the direct value. No need to calculate. Okay. So this is the Q. And now because this is the Q means heat energy. So as per this assumption, whatever the electrical energy you are providing, that total electrical energy E is equal to Q. And we know that E is equal to P into T. What is P? P is the power. And T is the time. Okay. So E is equal to P in T. And what is here? Q. Means can we write? This is, so this line you can write as, what is Q? 0.120 multiplied by 2500 into 28 is equal to P into T. What is T here? See here. From here to here. So here the temperature is 48 degrees Celsius. And what is the time? Time here is 120. So time is 120 second. It is in second. Okay, so 120. So P is equal to what? P is equal to 0.120 multiplied by 2500 into 28 upon 120. So when you will solve it, you will get as 70 watt. Okay. So what is the power? Power is 70 watts. So we have solved the first part. So we have already found the power of the heater. What is the power of the heater? 70 watt. This is the answer for your first part. Okay. Now we'll come to the second part. The melting point of the sample. Melting point. Melting means what? Melting means phase change. Here the phase is changing from solid to liquid. So this phase change or a change of a state occurs at constant temperature. So this is occurring here. It means this is occurring at 48 degrees Celsius. So what is the melting point, melting temperature of the sample? 48 degrees Celsius. Okay, because this is occurring at constant temperature. So this is your constant temperature. And it is changing phase from solid to liquid. So here, if you will see this, for this portion, it will be in solid plus liquid, both the states. And here for this it is solid phase, and for this here the whole melting process is complete. So in this part it will be in liquid phase. Okay, liquid phase. So now two problems A and B we have solved. The power of the heater is 70 watt. The melting point of the sample is 48 degrees Celsius. Now we'll solve the specific latent heat of fusion of the sample and the D part also. So first of all, we make some space for writing. Okay, so let me erase it. We'll make some space for writing and we'll solve the part C. Correct? So here we are going to use the concept of latent heat. And here because there was temperature rise in part A, so we use the concept of a specific heat capacity. Q is equal to MC delta T. Okay. So mass here everywhere, here also mass will be used as 0.120 kg. Here also 0.120 kg. Here also 0.120 kg. Because the mass of the substance is, mass of the solid is 0.1120, and the same substance is being converted from solid to liquid. Correct? Yes, so now we have already made the space for writing. Okay. So now come here. See that a specific latent heat of fusion of the sample. So here what is happening? Here this is fusion. This from here to here, what is happening? Fusion or melting, you can say, or melting. Here the solid is being converted into liquid. So this is the whole process, and this is occurring at constant temperature, and that temperature is 48 degrees Celsius. Correct? So we already know that the phase change from solid to liquid or liquid to gas occurs at constant temperature. So here in this case, solid to liquid means fusion, and this is occurring at 48 degrees Celsius. This is the constant temperature. Okay. So here, whatever heat energy is being supplied, or whatever electrical energy is being supplied, is being totally utilized for heating, means converting this 120 gram of solid into liquid. So for this period means from 120 to this is 560. So 120 to 560, during this period, there is only change in phase, no change in temperature. Okay. So when there is phase change, means here we'll use the concept of latent heat of fusion. Okay. So whatever heat, what is the heat energy here? Time into power. Now we have already calculated power. So power into time. So what is the power? 70 watt. Into what is the time here? 560 minus 120. That is 70 watt into 440 second. So 70 into 440. And watt into second is what? Joule. Correct? This is your energy. And now this E is equal to Q because there is no loss of heat to the surrounding. So we write Q is equal to ml in case of LF, latent heat of fusion, here in this case. So what is LF? LF is equal to Q upon M. What is Q here? It is E, or E upon M, you can write. So what is E here? E here, 70 into 440 upon what is M? M is equal to 0.120 kg. So after calculating it, you will get it as latent heat of fusion as 2.6 into 10 to the power 5 joule per kg. Okay. So now we have already got the latent heat of fusion, and that is equal to 2.6 into 10 to the power 5 joule per kg. We can write here 2.6 into 10 to the power 5 joule per kg. This is the answer of your C part. Correct? So we have solved this also. Now we'll find the specific heat capacity of the sample in the liquid phase, means this phase. Okay. So here again we'll apply Q is equal to MC delta T, because here also there is temperature change. Okay. So just we'll erase it and make some space for writing. Just a minute. Hardly it will take 1 or 2 minutes. So here in this case, we are going to solve the last part, that is D part, and it is when the whole solid has been converted into liquid, and whatever electrical energy you are supplying, that electrical energy is being utilized in raising the temperature of the liquid. Correct? So you don't know the specific heat capacity of the liquid that we have to find. So we can find with the help of this formula, Q is equal to MC delta T. Correct? Just a minute. Q is equal to MC delta T. And here also, the assumption is very important. There is no loss of heat to the surrounding. Means whatever electrical energy we are supplying, the whole energy is being utilized in raising the temperature of the liquid. No loss of heat to the surrounding. Okay. Actually, we are talking about the ideal case, but normally it doesn't happen. There is some loss of heat to the surrounding, but that we are not considering here. Okay, as per the question. Okay, so we'll come to the D part. So in D part means this is the last part. So here, this is your liquid. From here to here, it is in liquid phase. Liquid. So whatever heat, whatever the energy you are supplying here, that energy is being utilized in raising the temperature. So see here, this straight line shows that the temperature is rising, and this temperature is rising from 48 to, it is 56, 48 to 56. This is 56 and this is 48. 48 degrees Celsius. This is 56 degrees Celsius. So here T2 is equal to 48 degrees Celsius and T3 is equal to 56 degrees Celsius. So what is the delta T in this case? Delta T is equal to T3 minus T2. That is 56 minus 48. That is 8 degrees Celsius. Okay. So we'll use the formula. Here also, there is no loss of heat to the surrounding. Means whatever electrical energy was supplying, that is equal to the heat energy. E is equal to Q. And we already know that because this is the case of temperature rise. So Q is equal to MC delta T. And C for what? C for liquid. C for liquid. Okay. It means a specific heat capacity of the liquid phase is equal to Q upon M delta T. Or you can write Q is equal to E. So E upon M delta T. You can find E. E is equal to what? E is equal to P into T. What is P? P is the power. What is T? T is the time. So P is the power means 70 watt into what is the time? Time is equal to, see here, this is the time 560 to 600 means 40 seconds. So this is 2800 watt second or joule. Okay. So you can write CL is equal to 2800 upon M is what? 0.120 multiplied by delta T is what? 8. Correct? So when you will calculate it, we'll make some space here. This part was from the earlier question, earlier part. So we'll erase it. So what we are getting it here, CL means a specific heat capacity of the sample in liquid phase will be 2800, 2800 upon 0.120 into 8. And after calculated, we are getting it as 2.9. I have already calculated it. 2.9 into 10 to the power 3 joule per kg per Kelvin. So this was the last part, that is D part. So we have already solved it. Okay. So D part also 2.9 into 10 to the power 3 joule per kg per Kelvin. So just remember the unit of a specific heat capacity also. The unit of a specific heat capacity is joule per kg per Kelvin. Okay. And the latent heat will be joule per kg only. Joule per kg only. Correct? Because there is no rise in temperature. So now we have solved all the part A, B, C, D, which was based on the thermal properties, a specific heat capacity, latent heat, and a specific latent heat of fusion. Okay. So today we'll now stop this class today here only, and we'll meet in the next class. Okay. Till then. Okay. Bye bye.